Looks like all of them are overseas already, yeah? Oh, there's no choice then. Unfortunately for Quentin and Trafford, I think the first part here is a lot of it is HL. I guess I can just breeze through it since I don't know, like not sure if anyone's yeah. Okay. Is it that a lot of them are having tutorials in school? Do you know if anyone until what time? Hmm. Okay. No, I'm just worried. Then that means that then a lot of people might just turn up on Thursday. Then if they do that, then Thursday will be overcrowded again. Well, no choice. Okay. What was the last thing we did? Yeah. So have we done the example here? Huh? Haven't we? We hadn't done the example of modulation. We hadn't done the ratio. Isn't it like 4 times? Yeah, we did this, right? So we already determined what is the width of one slit, right? Okay. So again for Quentin and Trafford, let me just finish up with diffraction grating first before I go into standing waves, right? Yeah. We're gonna have a bit of a problem on Thursday if that's the case. I'm not too sure. Okay, that's fine. All right, let's start. So what happens when you increase the number of slits from 2 slits to 8 slits, right? And then further down to 16 slits. So what's the effect when you start increasing the number of slits? So Wei En, I think this one you have to pay attention to it, right? So you have 2 slits, right? The pattern looks like this. You have 8 slits, the pattern looks like this. You have 16 slits, the pattern starts to look like this, right? So what's the how do you describe what's happening here? Why is the intensity increasing? Right, so you can see that basically if you increase the number of slits from 2 slits to 8 slits, right, the intensity becomes 64 times. So obviously these graphs are not drawn to scale properly, right? Double slit, this one is 4 times the intensity, right? 8 slits, the intensity is 64 times the intensity, and then when it's 16 slits, the intensity is 256 times, right? Any reason why? Why does the intensity do that? Like why is it double slit? Why is it 2 slits and then yet it's 4 times the intensity? Intensity is proportional to amplitude squared. Yeah, proportional to amplitude squared. Yeah, hi. There's only the two of you, I think, but the rest of them are all online. Not sure why. Do you collect any data? You collected data. You have their data as well. I think I'll probably have to do the two of you the data after class today. Yeah, I'll just try to see whether I can manage the both of you your datas. You're okay with stay, right? Okay, can. All right. I may have to end around 5 though. So even though I said the lesson is going to be 2.5 hours, I think I will just do what is needed, right? And then I'll just move on. Okay. So very quickly, right? The effect when you increase the number of slits is basically, right, three things. Number one, bright fringes becomes narrower. Number two, bright fringes becomes brighter. Number three, dark fringes becomes wider. Okay, so those are the three effects. Okay. So what are the three things again? Bright fringes becomes narrower. Bright fringes becomes no dark bright. Okay, what are the two things that happens to bright fringes? First one, it becomes narrower, becomes brighter, and then the dark fringes becomes wider, right? So these are the dark fringes. Now we recognize that these are dark fringes because they are not there. There's no complete constructive interference. So if you look at one of these bright fringes here, which is like 64 times the intensity, that's basically 8 slits doing constructive interference all at the same place there. Everywhere else, you see tiny little bumps here, right? That's because there's incomplete constructive interference. We'll just treat that as destructive interference, okay? Right. Of course, the real minimas are at the bottom here, where the bumps hit the line. Sorry, those online. I need to realign my camera again. Oops. Hey, people just keep on knocking into the camera, but it's okay. It's not for me, guys. It's for you. Right. The cameras are not aligned, then you're the ones who don't see the real picture. Okay. So you see all these little, like, where it dips down to the bottom, that's a minima, that's a true minima. Like there's a slight little bump there. That's not a completely constructive interference. So that's kind of like a incomplete constructive interference, right? So I would imagine this something like this. You see 8 slits, right? 8 slits. Now at the bright fringes, all 8 of them are constructive with each other. That's why you get a very bright fringe here. Then you see the next one, which is this little bump here, which is a little bit high, right? That's like 7 constructive but 1 destructive. Then the next one is like 6, 2. Then the next one is 5, 3. Then 4, 4 cancel each other out. So the true minima is all the way at the middle there, right? If you can see the true minima is all the way at the middle here, right? And then afterwards you got your 5, 3, 6, 2, 7, 1, and then 8 again, right? All 8 constructive again. That's why you see all those little bumps in the middle there like this. Okay, so we call this whole thing, right? Just to give you a bit of nomenclature, we call this whole thing a dark fringe. This is a dark fringe. You understand that? Right? That whole thing there is a dark fringe. The whole white thing there is a dark fringe. We okay? All right. And this is a bright fringe. However, let me just tell you something, okay? IB over the years have under I think maybe 2 or 3 instances, right? Slipped in this weird phrasing, right? They call these primary maxima. These are called the primary maxima. Okay, they call these primary maxima. All right. I mean, in our language, what do we call the central one? We call it the central maxima, right? N equals to 0. Then this one, what do we call? We call it the first maxima, first order maxima, n equals to 1. Correct? Okay. But IB sometimes they call these orders of maxima, right? The primary maxima, while these little bumps, they call them the secondary maxima. Right? So they call these little bumps secondary maxima. secondary maxima, which is a bit misleading because they're not true maximas at all, right? They are like kind of like they're incomplete. They are underdeveloped, all right? So that's why they're a little bit stumpy here like this. Look at that, all right? So what you have is secondary maxima, and therefore we just regard the whole region here as a dark fringe, right? The effect becomes even more pronounced when you increase the number of slits. So let's say you have 16 slits, right? Then your bright fringe is really bright, okay, 256 times the intensity, and then you have a lot of a lot of destructive interferences in between, all right, a lot of destructive interference in between. You have a very, very small secondary maximus now, but this whole region here, we just consider it as a dark fringe, right? So this whole bracket here, we just consider as dark fringe, right? So what are the three effects again? Bright fringe becomes narrower, bright fringes become brighter, and then dark fringes becomes wider, not darker. Dark fringes are already dark, right? So you get the idea. Okay. So then, of course, the question will be, right, does modulation affect diffraction grating? The answer is yes, right? So sometimes you can see diffraction gratings having this single slit effect as well, all right? This has only come out in IB like once. Like there was one time they came out with this question, and then they asked you like, oh, why is the fringes behaving like that? Then the answer is just because of modulation. Other than from that, I haven't seen this happen before again. All right, I think mostly we keep seeing this question like this. I believe this was in your promos, was it, or was it in your CTs? Was it promos or was it CT? Promo? Yeah. I think one of them. Yeah. So yeah, this is a very popular question from IB. Like sometimes I see different schools also reuse the same diagram that I'm showing you here. It's kind of weird, right? I'm just thinking, why don't you be like a bit creative and then just use like a picture like this, for example, right? Don't stop showing them the same thing. Use this one now, just copy and paste this thing here, right? Anyway, so there we go. So what we want to do is I want you to draw the setup, all right? And I want you to be very careful with the angles, with the details. So you have to draw this a little bit carefully, right? But before I draw it to you, right? Those who are here today, Wei En, I think you need to see this via pictures. So I'll get them to take a picture. Yeah, you help me do a picture while I demo it to them here. Okay. Are your glasses blue filter? Huh? You don't think so? You don't have blue filter glasses? Wait, hang on. Take out your glasses. Face it upwards. Face it upwards. Okay, so you see the laser light. Oh wow, you don't have blue filter. What filter do you have? You make your your glasses makes it more blue than violet. Like this is violet, right? Then you go over and it becomes blue. So yours has a violet filter. Yeah, your glasses have a violet filter, not a blue filter. That's so strange. So some of the blue filter glasses, right, it completely disappears. Let me show you. That's so strange. What? Where do you buy your glasses from, man? So these are my blue filter glasses. Right, so something like this, right? You look at that? The difference. Can you help me? Could you help me take a video of it? Yeah. Sorry. Do you mind sending it in the group chat? You can, right? Okay. So it's something like this. So these are blue filter glasses. Right, so when you pass the laser over, right, so there's something, okay, right, yeah, just send it. I'll add on words to the to context later. But you don't learn this anymore. You don't learn about blue filters anymore. It used to be in the old syllabus. What you do learn now is diffraction grating. Okay, so what I have is a blue laser. Right, a blue laser. Let me just show you what happens when I. Okay, I think I'll just show it to you here. No, I had to check whether or not you could see it. Because if you couldn't see, I would have asked you to take out the glasses, you see. Right? So this is the laser beam. Okay. So this is when you put a diffraction grating to it. Okay? Do you see? Oh, it's kind of hard to see, sorry. Hang on. Let me just try this out. Okay, how many fringes can you see? Huh?
Six.
Huh? Why you got 6?
1, 2, 3, 4, 5.
5, right? Which one's the central?
The bright.
Yeah, then the first order. Right, this one and this one. And then there's a very tiny one faint one on the end, right? Yeah, there you go. Right, there isn't anymore, I think. Yeah, there isn't anymore. I think it's just your your retina has a bit of laser burn to it. Okay, so yeah, could you send that? Thank you. Okay, So what we have is you got to learn how to draw the setup. So I'm just going to draw the setup for you. So this is your diffraction grating. Okay. So what's the diffraction grating? A diffraction grating is when you have many slits, right? You have many slits in the hang on. Wait. Let me just.
But no one go there.
Maybe.
Maybe I'll go there.
No, I don't know. It's just saying.
Oh, okay.
It's not expensive at all. I mean, I'll go and buy it. It's just that if I use it for then.
Oh, okay. No, because yesterday I just make them sit here, and also here only. Yeah.
Oh.
Yeah, nobody, because I don't let them touch anything over there. Yeah.
No worries, it's just because I can't use this now. Okay. Thanks. Okay. What's the diffraction grating? Yeah, multiple slits, right? Okay. Now these are diffraction gratings, right? I mean, take care of it not because it's expensive or anything like that. It's cheap, but it's just damn mafan for me to go and order again and then wait for delivery and all. Yeah, it's just the trouble of it. No, so they don't look like, right? Okay, so for those who are online, come. For those who are online, all right. I mean, just Wei En actually, because the other two really don't. Oh, Wei En and who? Zaire. Okay, right. So this is the diffraction grating, right? So you can see the diffraction grating here, right? It looks like a piece of plastic actually, right? So, but it is a diffraction grating because you don't actually need physical slits, right? So obviously we keep thinking slits is like a physical slit, there's a hole or anything like that. What happens is this is a special type of plastic, right? Where the polymer chains, you all understand organic chem, right? Polymer chains are stretched. So as you stretch the polymer chains, they make lines, okay? So there's microscopic lines on the film, right? And then when light passes through these lines, right, each of these lines act as a diffraction grating. Okay, so the effect, you can't really see it directly. I'll show you why later, right? But that's what's happening here, right? So when you shine a laser light, right, into the diffraction grating like this, right? When you shine the laser light into a diffraction grating, right, it will diffract and it will give you the pattern. So the question is, how does it look like then? So how did it appear just now on the paper? Like, how does it look like? Yeah, so I shown the laser into the diffraction grating, and then there was a pattern on the paper, right? Like, how did the pattern look like just now? Okay, so yeah, essentially we're just going to assume that they're all the same. They're the same intensity at first, but this is the pattern you saw. Okay, this is the pattern that you saw. Right, there's one thing that I'm trying to do here. I'm trying to ensure that you see that the second order is slightly further away. Right, yeah, there you go. Right, so this is the pattern that we were seeing just now, and I think you sent the video out just now. Right, so this is light on diffraction grating, right, and then this is the pattern that you see. Okay, right. So there you go, right? What's the difference then with regards to the pattern? Let's say I compare it to double slit. Let's say I compare this pattern to double slit. What's the difference to double slit pattern? Yeah, what's the difference of this to double slit pattern? So I'm trying to make you recall this because these are the things that once you learn, you understand, you don't have to revisit this again until later. Unless your memory is really bad, but I don't think so. So double slit pattern is what? It's like the fringes are a bit wider, right? Correct. The fringes are a bit wider. Okay. The fringes are a bit wider. And the fact is that double slit, the fringes are all equally spaced apart. Right? The fringes are all equally spaced apart. This is not equally spaced apart. Right? So where you have the right fringes, the first order is here. Then the second order is like further away. Okay? Right? That's a key difference, right, between the fringes of double slit to diffraction grating. That's one of the biggest difference. Okay. Then the next thing is the equation, right? You will see this equation in your data booklet. D sine theta equals n lambda, right? D sine theta equals n lambda. You wouldn't see the other one. The other one is this: tangent theta equals x over d. Because this is one of those equations you need to memorize, right? They make you memorize it. Okay. So let's break it down first, right? What is d? What's small d? Distance between the two slits, right? Okay, so distance between any two slits, because now that you have diffraction grating, you have multiple slits, so the distance is what we call the slit separation, or we call the line spacing, right? You could also call it a line spacing, right? Line spacing, slit separation, grating spacing even, right, and all that. Now, I passed you all some diffraction gratings on the table, right? You have that sample there. I want you to look around it and see whether you can get any information regarding small d, right? So for those who are online, right, I'm just going to show this to you, right? Can you find any information regarding yeah, 1,000 lines per mm? You know what that means? It means that if you take a ruler, right, you take a ruler, okay, and you place your ruler across it like this, right, within 1 mm of the ruler, right, 1 mm, that's 1,000 lines. That's crazy, right? But that's achievable because it's a polymer, right? There's plastic chains, right? And they have stretched 1,000 plastic chains within 1 mm of width. So I'm gonna ask you this: so what's d then? So if let's say the brand of the diffraction grating tells you is 1,000 lines per mm, then d will be equals to, so 0.001 meters divided by 1,000, and therefore d is equals to 10 to the power minus 6 meters. We got this, yeah? Yeah? So we understand this, great. Hang on, I think today I feel like wearing my glasses. Okay. Then, let's look at n. What's n first? I'll go into detail in a while, but what's n? N will be the order, right? So you got n equals to 0 in the middle, n equals to 1 here, and n equals to 2 here, right? So 0th order, central maxima, first order, second order, right? Slightly further away. Lambda will be the wavelength, duh, right? So this one we understand that, wavelength. Right, again, before we go into detail, let's talk about, okay, you know what, let's talk about big D then. Big D is like the same as double slit, distance from slits to screen. Okay, theta. Theta will be the angle from the central max, Theta will be from the central max to whichever order maximum that you're looking at. Okay, so let me just give you a bit of a heads up like this. So theta will be this one here, right? This is considered as theta 1. This is considered as theta 1, right? This is the first order angle, okay? But theta in diffraction grating is not constant, okay? And in fact, if you want to find theta 2, right, that means the angle to the second order, it is always measured from the central maxima. So for theta 2, right, is measured all the way, right, all the way from central maxima. So this theta here is different from the theta in single slit and from the theta in double slit. That's why I say same but different. Okay. In double slit, theta is what? From what to what? From maxima to maxima, right? Correct or not? Theta for double slit is maxima to maxima. How about theta for single slit? Central max to first minima. Good. Right? You're getting it ready. But for diffraction grating, the theta is from central max, yeah, to whichever end maxima they are looking at. Right? So you realize, shit, it's all different. Okay? So you cannot have the same theta for all three scenarios, right? It is different. And that's why I'm doing this. Because I probably nobody told you that before. Right? And probably like you're like kind of like mixed it up all up before. Like, so there's three things: single slit, double slit, diffraction grating. Okay, great. So we cleared that up. How about X? What's X? Yeah, the distance between the central max to the whichever order you're looking at. Okay. So x1 is from central max to first order, linear distance. X2 is from central max to second order, right? Linear distance. There you go. Right? So these two equations, just take note, just remember this equation is not in data booklet. Okay. So yeah. Then the next thing I want you to draw is draw the graph. How do you think the intensity graph will look like? The intensity graph. How would the intensity graph look like? Right, so you will have one spike here, one spike here, one spike in the middle, one spike here, and then another spike there. Okay, so this is how the graph will look like. You know, because they are very narrow fringes, they are very wide dark fringes. Okay, and then your this central fringe is right in the middle. First order is closer, second order is further away. For diffraction grating, the angle and the x are no longer proportional to the order. Like, you know, double slit is what? Double slit is, if let's say you're looking at the fourth order, then you just times 4, right? The x times 4 or the theta times 4. But for diffraction grating, you can't do that because the angle is no longer written as theta only. There must be sine theta and tangent theta. There's no small angle approximation for diffraction grating. Why?
All the angles from them are typically close to each other and it's like
Right? Because theta is not small. Right? For diffraction grating, theta is not small, so we cannot do small angle approximation anymore. What did we do in the single and double slit? We had sine theta, we approximated to theta. If we had tangent theta, we approximated to theta. Down here, we can't do that. So for diffraction grating, you cannot, right? You cannot approximate it to theta. So theta is no longer small. We good? Good. Diffraction grating is one of the most important experiments in physics. Yeah, I know, it sounds ridiculous, but it is. Right? It is one of the most important experiments in physics. Right? In fact, you should understand what's the primary purpose of diffraction grating. What do we use diffraction grating for? Okay? Right, so there are two purposes, two main purposes. Number one is to determine lambda of unknown light. Right? Determine the wavelength of an unknown light. I have a laser here. Right? Look at the laser, there's a label on it. The label will tell you what's the wavelength. What if I peel this label off? Right? I peel it off. Right? There's no more label, you don't know what's the wavelength. Okay? And if you don't know what the wavelength is, how are you going to find the wavelength? We're going to have to use the diffraction grating to help us find this. We're going to have to use the diffraction grating and use these equations to help us find the lambda. Okay? So let's go through the process of how to use a diffraction grating. Right? I don't think a lot of people are doing the diffraction grating experiments this time around. I don't know why also. There's this diffraction grating salt solution and then finding the wavelength of the light in the salt solution or sugar solution. Nobody's doing that. Do you see anyone doing that? Like a tub of water, then they add sugar into it and then put diffraction grating inside. You have someone doing that? You see your friend doing it? Yeah, okay, that's great. Right, so basically, right, what we are trying to do is we are trying to find the wavelength of the light inside the solution by using a diffraction grating. You get what I'm saying? Yeah? Okay, how do we do that though? Right, remember the image I showed you? Oh, hang on, guys, wait. Hello? Yes, I am. Is there an emergency? Okay. Oh, okay, bye-bye. Oh, bye-bye. Anyway. What? What was I saying? What was it used to do? No. Yeah. We are trying to find the wavelength. We are trying to find the wavelength of this light, right? Okay, good. Let me show you again. Pull out the paper and the diffraction grating there. Okay. So you see, right? So in order to find, okay, hang on, I back up a bit. Sorry, back here again. I was trying to do the demo. In order to find the lambda, what do you need? Because you can't measure wavelength directly, right? So you need what? From this equation, you need n we can choose, right? Let's say I choose first order. Okay, so n is 1. Then what do I need? D. Can we get D? D is from where? The diffraction grating itself, right? Okay. Theta? Can you measure the angle? Can you measure the angle? Let me show you. Can you measure the angle? See this? How do you measure the angle? You can't, right? It's not like you can put a protractor, right? Okay. So while on diagram, it looks like, oh yeah, the angle is here to here, right? But in real life, when you have a diffraction grating and a laser and you shine it onto the screen, you can't really put a you can't really put a protractor and go and measure the angle. So you can't measure the angle. But what can you measure? You can measure the distance. So with a ruler, you can measure the linear distance from the central max to the first maxima, right? And you measure that distance. You can measure this distance from screen to slits, and get theta. That's how you find the wavelength of unknown light. Okay? So you measure X, you measure D, you calculate theta, you sub in here, theta with the line spacing and the order that you are looking at, you can calculate the wavelength of an unknown light. So even if the label has been torn off, right, you can use that to find the wavelength. Okay. Diffraction grating will come back again in E1, E5. Yeah. Right. So it's important that you know what's the use of it. Right. First, it helps you to find the wavelength of an unknown light. So some people might be doing this for IA, especially those who haven't decided on RQ yet, right? Or maybe haven't even gone to the lab yet, right? And maybe for the next those who are in January, you want to do this, yeah, go ahead and do this one also. It's also okay, right? I believe there are not many people doing it, so if there's not many people doing it, you can go ahead and do it, right? But it really depends on the rotation of teachers. Some teachers are like they when they see that this one, they are more happy, and then like the other rotation, when they see this one, then they're like, oh no, it's a gimmicky type of experiment, like, you know, it's just weird, right? These people cannot have the same standard. Okay, the second use of diffraction grating is to split colors. All right, we're going to diffract colors. Lasers are what we call monochromatic light. Right, lasers are monochromatic light. So if you have a laser, it's only of a certain wavelength. Right, plus minus, okay? But white light is what? What is white light? A whole bunch of colors, right? Name me the entire list. Why are you going backwards? Why you say purple? Orange again. Indigo violet. Blue, Roy G. Biv. ROYGBIV, right? So there's no purple, huh? However, there was one question from IB long ago, very annoying question, where they used the word purple, and then in the examiner's comments, they said that students should be aware that there's no such color as purple. Purple is a mix of blue and red. Right? Yeah. So that's what happened like long ago. That was long ago, and I think there was an uproar on that. So they stopped doing that nonsense anymore. Just be aware, okay? So purple is not an actual color. Purple is a mix of blue and red. Okay. So if you look at the next, the last pages, right? What happens here is that you actually do get the diagram where, right, white light is being diffracted into its separate colors. So what you want to do is you want to just indicate that this is white light. Okay. Now for those who are SL and you kind of like you realize that, hey shit, you know, actually if diffraction grating is something that you can do, right? Why don't you do it, right? because it's not in your syllabus, and then yet the idea of it is very similar to double slit. Okay, so it's not something that's like, you know, beyond you, right? I would suggest that maybe you can try it out, right? I think I do have some sample IAs inside my IA folder that has the diffraction grating. I only picked out the very high scoring ones, like the I think the 20s. I don't know whether I gave you any 19s. Were there any 19s inside? Guys, don't worry, okay? Anything 19, 20, 21, 22, and very rarely I get 24, right? Anything above 19 is already great, right? 19 and above, 19 about 24 is how many percent? 19 about 24 is 19 divided by 24. That's 79% already. Yeah, right. I think the standard I usually have is everything is above 17, right? 17, 18, right? But most of them end up being 19 and above. The weird thing is this. So in-house, the teachers will mark my students around 18, 19. But by moderation, they will moderate it upwards to 19, 20, right? So that's the average score, which actually kind of tells you that your teachers are trying to suppress your IA scores. But when you compare it to the global average, like the physics IAs that comes out from, you know, like by our standards is much higher than what they expect by the IB themselves, right? So they always moderate it upwards. Langlit, on the other hand, will be moderated downwards. I'm sorry about that. TOK as well. Did you hear the TOK moderation? It was ridiculous. In-house marking is 10, moderated down to 7. What the hell is that about, right? I think they are trying to suppress the number of 45s that we get in ACS. Actually, I think it's a very school-specific target, the moderation, right? But I don't know, right? Yeah, we'll see. Okay, so anyway, this is white light. So what you see here is white light being split by the diffraction grating into different colors, right? When you have a rainbow, we don't call it a rainbow in physics, we call it a spectra. So this is what we call the first order spectra, then a gap, which is the dark fringe, then the second order spectra. So obviously inside your notes, they're all black and white. I'm sorry about that. So if you have a red or blue pen, you can just color the red and color the blue, right? Use the blue as the violet, you know. Blue and violet are actually very, very close to each other. So you just color it onto your diagrams. Okay. I used to provide markers, but then the markers tend to seep through the paper and make a mess out of the notes. So I need to go and find, what is it? There's this special type of marker called acrylic markers or something like that. Acrylic markers that don't seep through the paper. I don't know, man. I need to go find one of those. Or I should just go and find rainbow paper. And then just do some art and craft, cut and paste. Okay, but there you go, right? Notice a couple of strange things. Number one, the central maxima is... Why? Why is it white? There you go. Constructive interference of all colors, white in the middle, right? This is first order maxima, this is second order maxima. Notice which color tends to bend the most. Red bends the most, right? For each of the orders, red bends the most. Why? So you got your d sine theta equals n lambda. Okay? D sine theta equals n lambda. Right, so there you go. This will be the reason why you can see like only this spectra here. Now, very more advanced questions, they will ask you questions like this. What's the highest order of spectra that you can see? Right? So let's say they ask you for highest order highest order of spectra. Right, highest order of spectra. Which color should you be checking and what angle should you be using? You should check the red one, and which order should how many degrees? What's the biggest angle you can get? 90 degrees. Okay, 90 degrees. So I'm gonna give you an example now, right? So I'm gonna tell you that this is a 100 lines per mm grating. 100 lines per mm, right, per mm grating. I want you to tell me what's the highest order of spectra that's visible. Yeah. So when it comes to this kind of questions, you just assume that there's a curved screen like this. So then that means that if you want to observe the highest order, you can look at the 90-degree mark, like that. Okay. So you can look at the 90-degree mark like this. Okay. So if you want to find the highest order of spectra, d sine 90 degrees equals to n max lambda. Okay. D will be 0.001 divided by 100 times 1 because sine 90 is 1, n max. And what is the lambda of red light? So you have to go look for the wavelength of red light. Do you have that? Go and check the data booklet. Right. So it's 14, yeah? Now the tricky bit to this is this question here is a different question. What are the max number of complete spectra observable? Right? This question is asking you for the highest order. This question is asking you for the number of complete spectra that you can see. Right? So the thing is this. The one in the middle is not a spectra, but it is a bright fringe. But the question did specifically ask for spectra. So if you consider spectra as a rainbow, the one in the middle is not rainbow. The one in the middle is white. Okay? Spectra is this whole thing here. So the number of complete spectra that you can see will be 14 on this side and 14 on the other side. So a total of 28. Right? For a total of 28. Right? Complete spectra observable. Right? So 28. Because the max number is 14 and therefore this one is 28. Are we okay on this? Yeah? If they give you monochromatic light, let's say they give you a red laser, okay, a red laser, and they ask you how many bright fringes can you see, then it'll be 28 plus 1 in the middle. Right? Just be aware of that, right? I mean, there's many different kinds of diffraction grating questions. Right? Then the next one is, do the second and third order overlap? So they're asking you about overlapping, right? Will the second and the third order overlap? Right? And the answer is you have to check. So if you want to check for overlapping, whether the spectra overlaps, okay, if you want to check for that, okay, what should you check for? So when it overlaps, right, you need to check the lower order, you need to check the red color, and for the higher order, you check its violet. Right? So you got to check which one has a bigger angle. If red of the lower order has an angle bigger than the violet of the higher order, then that means it overlaps. Okay? So, do lah. Right? So that means you need to check what? So second order, you check which color? You check the red. Third order, you check the violet, right? D sine theta equals n lambda, you check the angles, right? So theta 2 red and theta 3 violet, right? You see which angle is bigger, right? I'll leave that to you now, right? Use your data booklet, go and find the violet wavelength, right? Use the whole thing. Right, check the rate of the second order and check the violet of the third order, and then you let me know whether or not. Huh? So you're saying that the rate of the second order, the angle is more than the violet of the third order, and therefore it overlaps. Okay, good. There you go. Right. So yeah. So it's one of those questions where you might not understand where the hell are they, like, coming from, right? They have no idea, like, why are they asking me, like, what kind of weird ass question are you asking me to do? Like, why are you asking me to check whether they overlap, right? So once you understand that, like, there's such a question and how to tackle it by looking at whichever color that's specific to whichever order, right? Then suddenly you know how to do this question already. Okay, right? So yeah, I think diffraction grating, there's really not much else. Everything else is just practice. So I'm gonna leave it to you to do practice. All right. I've got some of them who are already on practice now. It just came to my attention that some of them might be at tutorials today in school. Oh my god! Like who? So you're one of the good students, ah? Oh, oh shit! Did you just throw Matthew down the bus? Oh yeah, that's true. That's true. Not that he's the delinquent, right? Okay, yeah. Just to set the record straight, right? Okay, right. But how about the rest though? Like was Emma there? I saw Emma. Don't think so, right? Emma, Cheng Hui. Yeah. So that means that I guess they don't need this then. I think they just wanted to clarify the single and double slit. Okay, that's fine. Right. I was just wondering, like, oh, might I have underestimated the number of people coming today and overestimated the people coming today and underestimated the people coming on Thursday. Anyway, so this is an actual IB question. This is diffraction grating. All right. The idea here, the style of this question is very similar to the one that you did before for double slit, right? It's pretty much the same thing, right? So we have light going into diffraction grating. This is just part of it. There are three slits that's being shown here, right? Three slits, right? V, W, and X. Light waves are diffracted through an angle to the second order diffraction maximum. So this is your n equals to 2. N equals to 2. So they will go on and then they'll form the second order maximum there. Right? What does the n equals to 2 represent again? What does the 2 represent? I mean second order, yeah, but what does the number 2 represent? Like 2 of what? 2 wavelengths. Right? So there's a path difference of 2 wavelengths, right? Okay, so for diffraction grating, there's many slits. If there's only 2 slits, so we go back to the 2 slit example. Let me just show it to you, which is here, right? Right. Remember, we were trying to do this. We were trying to do this differentiation. We were trying to do these derivations, right? Okay. And then I said that these two are headed towards what? N equals to 1, right? N equals to 1, right? And then what you do is you drop a perpendicular from one source to the next source to the other light here. You drop a perpendicular, and then what happens is that what's this, like, you know, what's this here then? Yeah, one wavelength, right? Yeah, one wavelength apart. Okay, you get what I'm saying? Right? Did you label this already from the last time? Yeah, you did, right? Okay, so that's one wavelength apart, right? I mean, that's how we derive the second or the double slit equation as well, right? So that's n equals to 1. But in this particular question, in my example here, right, I'm doing diffraction grating and I'm doing 3 slits, 1, 2, 3, right? 1, 2, 3, and the question says second order, and therefore n equals to 2. So what does the 2 represent? Two wavelengths, difference between what? Between two sources, right? So which of these sources? Okay, between this one. Okay, let's say we label 1, 2, and 3. One, okay, not 1, 2, and 3. A, B, you know, okay, like X, W, and V. Let's say between W and V, all right? The light rays coming out from W and the light ray coming out from V. Which one is longer? Which one is longer? W is longer, right? By how much? 2. 2 wavelengths. So now we are showing 3 sources, right? 3 sources. So n equals to 2 represents 2 wavelengths apart for every adjacent source, right? Adjacent pair of sources. So if let's say between these two, they are 2 wavelengths apart. Between these two, they are also 2 wavelengths apart. So I'll draw it for you, right? So the 2 wavelengths is this one here. Sorry. Okay, so this is 2 lambda, right? That's the 2 lambda there. So between this light ray and this light ray, this one is longer by 2 wavelengths. How about between the middle and the top light ray? Also 2, but they didn't drop the perpendicular for you. So if you dropped it yourself, this is 2 light wavelengths. Okay? What they did drop for you is they intentionally try to trick you by giving you the dotted line here that joins between the first and the third one, which means that the total distance here is 4 lambdas. Yeah, there you go. Right? So in case you're wondering what you're looking at, right? But yeah. So this is your diffraction grating. The derivation of the diffraction grating equation and the double slit equation is very similar. It's very similar. So if you look at this triangle here, the pink one, right? This pink one here. This is theta. Do you see that? Right. So if you isolate that pink triangle there, like this one here is 2 lambda. This is d, and this is theta. Sine theta equals to 2 lambda over d. D sine theta equals to n lambda. Right, that's how the equation was derived. Okay, I didn't have to teach this last time until this question came along around May 2021 or 2022. Right, then suddenly, oh man, I have to teach you all how to derive this thing again, right? So it seems to be part of the core syllabus anyway. So yeah, there we go. Okay. Well, that's about it for this diffraction grating. I think the rest of it, the questions is doable on your own. I'll leave it to you, right? Since you already understand this. Oh, I forgot to do one thing. I wanted to demo for you how white light is diffracted with a diffraction grating. Okay, so this is for those who are here, and I think I need someone to take a picture of this again. All right, Adi, right? I need you to move to the chair there first. You just move yourself there first, because I need to stand under the projector. Let me just switch this off here. It's quite dark outside now, so you can see the colors quite obviously, right? So when there's white light, so right now the board is a white screen, right? Then I raise this thing all the way up here like this, okay? So if you notice, right, on the right side, you see that? No, on the right side, on the wall. On the wall, do you see that? Yeah, on the left side also, it's a bit faint because it's a bit bright over there, right? But you can see all the colors, right? Yeah. Can you do me a favor and try to zoom in and take a picture, including the part where my hands are holding the thing? Yeah. Just a picture will do. Right, you can see the colors? Yeah. There you go. Right. Yeah. So what do you notice about the fringe in the middle? What's the middle? The fringe in the middle. In the middle here. In the middle here. What color is that? White lah, right? So there's constructive, like there's basically no splitting of the colors there. Correct. That's the first order spectrum over there. I don't think so. I don't think so. I don't think there's a second spectrum. Simply because this diffraction grating, the lines are too close to each other. So the order that you can see is actually not a lot, right? Red doesn't appear, right? But what you can see is red is all the way at the end and violet is closer to the middle of the screen. Yeah. My projector lamp is flickering. I need to swap out the lamp one day soon. Hey. All these teething issues from time to time. Okay, thanks. There you go. Right, so I think diffraction grating, I'm done. So please remember the two most important uses of diffraction grating, right? One is to determine wavelength of unknown light because you need that for E1, E5, and then later on you need it to split colors for. Actually, you also need it for this E1, E5 also. Yeah, E1, E5 as well. Yeah. So these two, yeah, we need these two. Okay. All right, diffraction grating done. I will now move on to standing waves. I'll print out the notes for you now. Right, while y'all take a quick break. Standing waves. Oh, sheesh. Yeah, it's one of the worst, man, this one. Standing waves. Standing waves for everyone, yeah? Standing waves and resonance. Yeah? So there we go. Beep, beep. What? Yeah, thank you. Take some snacks then. Just go over there and take some snacks. I'm gonna take some M&Ms myself. Oh my god, did she draw the arrow on it? That's damn funny. Okay. Yeah, for the SLs, if you want to use anything to do with diffraction grating, yeah, you can. I mean, yeah, it'll be a good idea. I think I removed it because I don't know why I removed it, but I'm now gonna send it to you. But I need to find my Telegram first. Oh yeah, there you go. Can you take the notes and split half between the two of you? Hey, who are OGLs next year? You went for selections already, yeah? Oh, okay. Who else that we know of? You just said the Hounseless. Okay. So lame. Really? Like Jaden Wong, Jaden Liu, Emma, Cheng Hui. I'm gonna just list down the names then. Cause I wanna see who's gonna be like busy next year, you know? That's gonna be a problem, right? Who else is there? Let me see. Samantha, no? Shane. Yeah. Oh, you mean that? Oh, so we have some counselors with us. Okay. Who are the counselors? Oh, Jerry as well. Okay. Jovine? Oh. Oh man, all you guys are gonna be busy. Caris? Elsa? Janelle? Kayla? Rianne as well. Who? Eh. Okay. We're gonna have to go through the painful part of standing waves now. Okay. Standing waves is kind of painful, but I'll try to keep it short and sweet for you all. It's just that I'm just afraid of like Well, actually, yeah. You know what? I'm just gonna go. Just gonna jump right into it. Okay. What's the difference between standing waves and two source interference? Yeah, no. All you have to do is just say opposite directions. Yeah, there you go. So standing waves are just strictly those that you know the two waves traveling in opposite directions. That's like the most important part. Okay, so standing waves is just this. All right, so if you can see, right, you just zoom in here. Standing waves is just the two waves traveling opposite directions. Like, it have to be traveling like that. So I'm gonna ask you this, okay? Right. So you see, right? If you have one source here, right? If you have like one source here and another source here, and then I put a point P here like this, right? So what kind of interference can you get at P? Is going to be constructive or destructive, right? Okay. So like along here Q and then R, for example, right? Like you will get a series of maximus and minimus along the line. Okay. Is it a standing wave here? Yeah, it's not a standing wave there. You know what I mean? Like that's not a standing wave. Why is that? Why is it not a standing wave? There's maximus and minimus. Or that sounds like antinodes and nodes. Right? So the requirement for standing waves is that the two waves must be traveling opposite each other. What happens here is that these two waves are not traveling opposite to each other, traveling at an angle to each other. Okay? Yeah. So these cannot be standing waves. Like you can't form a standing wave in this region here. However, you still can get a standing wave from this picture. Where do you think a standing wave exists in this picture? Where do you think a standing wave can exist in this picture here? There's no reflector. I mean, everywhere around them is just open space. Where can you find a standing wave? I'm telling you that there's a standing wave in this picture, but like where? Between the two of them, between the two sources. So a standing wave can exist here. Right? It can, but it not necessarily always means that there will be. Okay? So there could be a standing wave here, right? And the reason is, right, these 2 point sources, the waves are traveling in all directions, right? So between the two of them, the two waves are traveling towards each other. So you could get a standing wave in the middle between the two sources. But there's still another requirement, right? And the requirement is that you got to have the right frequency. If you don't have the right frequency, you can't get the standing wave. All right. Okay, good. So there you go. Right. So that's the first idea. Right. So I'm just going to show you some animations, and I'm going to tell you that these animations are available online. So in case you need to review them again to see how standing waves are formed, right, it will help you a lot. But just remember that in the exams you don't get animations. Right. So I'm just going to show you some of the animations. So let me just take 30 seconds to pull this out. All right. So there we go. Right. So we have a kind of like a simulation and animation here. So what you see now is a traveling wave. Like why is this a traveling wave? Like why is this a traveling wave? It's really slow now, but it's still traveling. It's a traveling wave because the wave is traveling. I know it's damn dumb, but yeah, there you go, right? It's a traveling wave because the wave is literally traveling to one direction, right? You can see it's traveling from left to right. Okay? Now what's gonna happen is gonna hit a fixed end, right? It's gonna hit a fixed end, and this wave will be reflected back to the left side, right? So I only have one source. The source is coming from here. So this is the incident wave. It's gonna hit this end, it's gonna reflect, then you get your reflected wave. Does that fulfill our requirements? Right? So you will have your incident wave and your reflected wave superposition, and therefore you will get a standing wave, right? So let's see what happens as it goes along, right? As it continues to do that, right? So you see the reflected wave being formed right now. So now what we are having here is that incident wave is interacting with the reflected wave, right? And therefore the resultant wave, which is this black color line with the dots on it, right, is now creating this effect, right? Yeah. Right? So as it continues on and on and on, right? You should understand this. The incident wave and reflected wave, once they overlap each other fully, right, which they will in a short time, okay, you technically can't see them anymore. And what you get is this. Right? So this is a standing wave. Like what makes this a standing wave though? What are the features of this that makes it a standing wave? It's not traveling anywhere. That's why it's called a standing wave, which is why it's called a stationary wave. It's a stationary wave that doesn't seem to be traveling left or right or any particular direction, right? What do you notice about the some features of a standing wave that the traveling wave doesn't have here? Like what features of a standing wave does a standing wave have that the traveling wave doesn't have? You have this concept of nodes and antinodes, right? Look at this. There are some particles that absolutely do not move at all, right? They're nodes. And then you have some particles which have the biggest amplitude, right? Biggest amplitude, right? And that's another feature of your standing wave, right? The traveling wave doesn't have that. You understand what I'm saying? Okay, I'm gonna jump right into it because when I was teaching this from scratch in the past, I could have a lot of time to go through a lot of details. So I'm just gonna jump through some stuff and very quickly. So I'm gonna ask you some things like, for example, I want to ask you to check on the phase difference between the particles. Okay, I want you to look at the phase difference between the particles. Okay, so I want you to look at all these particles here. I'm gonna pause this thing for a while. 3, 2, 1, pause. I want you to look at all the particles between two adjacent nodes. See all these particles? This one, 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 this one. All right? Notice that only the one at the antinode position has the largest amplitude. Are all of them at their respective amplitudes now? right? Which whatever amplitudes they have, right? Do you realize that for standing wave, the particles, right? Not all the particles have the same amplitude. Only the antinode has the maximum amplitude. Everyone else that's not an antinode do not have the same amplitude as the antinode. The antinode has the largest one. Okay? But when they move, do all these particles move down together at the same time? Do they all move up together at the same time? They do, right? Okay, look closely. So I want you to look at all those particles again. So you just pay attention to these particles. For those who are online, right, HLSL, all of y'all, right, y'all have to pay attention to these particles here. You see all these particles here, right? And I want you to tell me, right, how do they move? Everyone move down, and everyone move up, right? Until maximum, different amplitudes, and then move down again until negative maximum, right? All different amplitudes, and then move up again, right? Okay, so I'm gonna ask you this. This is a very important question. They love to ask this question all the time. What's the phase difference between all these particles here? Everyone up, everyone down, then everyone up again, right? So what's the phase difference between all these particles? 0. They have 0 phase difference, right? Because they are moving at the same stage of oscillation, right? Everyone at their negative amplitude, moving to the negative amplitude, and everyone move up at the same time. Okay? Right. So between two nodes, all the particles have the same phase. The phase difference is 0 between two nodes. But you compare it to the adjacent section. So let's say you take the particles that are here, right? So all these particles here, you compare it to this section here, right? So you compare these two. So this one up, like that, and this one straight sides. You know what I'm saying? So what's the phase difference between these two sections here? What's the phase difference? Pi radians. It's pi radians. So for standing waves, if they ask you for phase difference, there's only two answers, either 0 or pi. Okay, standing, you want to write that down? Phase difference, right? Particles only got two kinds of phase difference, right? There are 0 phase difference for the particles between two nodes, and there are pi radians phase difference for particles between two adjacent sections of particles between two nodes. Right, write that down. Make sure you take that down because I'm going to move on quite quickly after this. Huh? Oh. I thought you raised your hand. Okay. Right. So you basically get your standing waves. But this is a very simplistic simulation. This was created in 2003, 22 years ago. The heck, right? And it's missing one important fact, right? It's missing the fact that you have to have the correct frequency, then you can do a standing wave. You cannot just get any old house standing wave, right? By just having one wave go in, one wave come out like that. That's not going to work, okay? All right. The next thing I want to do is, again, another website that you may have seen in school, right? Back in secondary school as well. Right, this simulation, this program, right? But the way I use it is a bit different. Okay, let me just show you. Let me just show you a typical traveling wave. Look at the traveling wave. The wave is traveling out of the door. Okay, so it's traveling out of the door. Okay, I will never be able to get a standing wave like this because I need the wave to come back. Right. So if I want the wave to come back, I need to either use a fixed end or a loose end, right? So there's a fixed end or a loose end. Now, a fixed end is also called a closed end. A loose end is also called an open end, right? So closed end, open end, okay? Now, you might be wondering what the heck is this? What the heck are those, right? So I'll just show it to you first. Hang on. Let me just... So a fixed end, right, is when you G-clamp it. So you don't allow it to move. And that's called a fixed end. A loose end is when you attach the end of the string to a ring and you let it move up and down the retort stand rod, like this, right? That means this thing can move up and down, right? That's the difference between the two, okay? But right now, I want you to pay very close attention, and this is something that I think I did in the last lesson, but some of you might not have noticed. Okay, we're gonna send a pulse over there. Okay, hang on. Right. So this is a pulse. A pulse is like half a wave. Right. This half a wave is now gonna hit this end, and it's going to do what? It's going to reflect back. Okay. So please take note. There are going to be two things that's going to happen. You're going to see two things happening. Number one, you will see the wave reflect back, going towards the left, and you will see the displacement of the wave go from positive, flip over to negative. Right? Okay, so look carefully. Right? Nothing too fancy, but that's what it is. Right? Then you see it happen again. Right, then let it keep on running a bit to let it form, like, form a video image in your head. Right? Okay, so the reflection going from left to right, right to left, right? You see this wave going right and then going to left. That's just called reflection. Right? That's called reflection. When the wave flips over, that's called phase change. Right? So every time you reflect from a fixed end, there's a phase change of pi radians, right? Because your amplitude goes from positive to negative or negative to positive, right? So reflection with phase change. It's in my notes, right? You can see in my notes, right? Oh, sorry, it will be not on this set of notes. It will be in C3, I believe, right? So I should just put it there. Wait, where is it? It's somewhere here in my C3 notes. Hang on. There, down here. Okay, there's a page 13 here. Okay. So when you reflect from a fixed end, right, there will be a reflection right to left. Okay. And then there's a phase change, positive to negative, right? So there's a phase change of pi radians. You get that? Okay, good. When it is a loose end, there will be no phase change. Let me show this to you. Right, it's just switch out to a loose end here. Right, notice what happens. Okay, so reflection fixed end, amplitude will change direction. Reflection open end, amplitude doesn't change direction. Negative still remains negative. Right, that one will flip over to positive. So when it comes here, it will be positive, reflect with positive. Means when you reflect from a loose end, no phase change. Right? This will help you understand for standing waves why closed end is a node and open end is an antinode. Right? We'll explain that in a while later. Okay, I'll just explain it now. What? Okay, do not use those words because that's just you trying to simplify it. Right? I mean, simplify is fine. Don't make it simplistic. Right? Use the words properly. So what we say is reflection at a fixed end has phase change of pi radians. Reflection of a loose end, there's no phase change, right? So it remains the same phase. Then that's it, right? So don't say upright or inverted or anything like that because that's gonna confuse yourself, right? So anyway, the words are all here as well, right? So don't need to rephrase it. It's just like that. Just remember it like this, okay? All right, there you go. Okay, so the amplitude has no phase change. All right, and I'll explain to you why now that you always get a node. All right. So what I do is I hide the standing wave. These are the incident and reflected waves again, right? Technically, you can't see them because they actually make the standing wave, and the result is a standing wave, so you cannot see them. But I'm just showing it to you anyway. Okay. So what you notice is this. You see this one? You see this red one? Positive, right? When it reflects, you should get a negative blue. And that's what's happening. So when the reflection happens, right? Positive red, negative blue, right? Or negative red, positive blue, correct? So what you have here at this end here, which is the fixed end, right? Okay, which is fixed end. The incident wave is always going to be one type of amplitude, and the reflected wave is going to be the flip of it, right? The phase change of it. And whenever you do that at the at a fixed end, what kind of interference you get? One positive, one negative, or one negative, one positive, what kind of interference you get? You always get destructive interference, and therefore at a fixed end, it's always a node because of the destructive interference. What if I switch it out to a free end? Right, let's say I switch it out to a free end. Yeah, let me do it a bit faster though. Okay, free end. Hang on, let me just also do it step by step. Okay, so this is a red incident wave. It's gonna hit the free end. So when there's a reflection, you see the blue. Where's the blue? What kind of amplitude does the blue have? Positive, right? There's no phase change, right? So you have a positive amplitude and another positive amplitude. They're interfering with one another. What do you get? You get constructive, and that's why for free ends, it's always an antinode, right? So you end up having an antinode like that. Okay, then you continue and all that. But no matter what, whether a fixed end or free end, you if the conditions are correct, you will always get, right? You will always get a standing wave, right? You always get a standing wave, right? Oh gosh, wait, yeah. Right, you always get a standing wave, and I mean, yeah. So the only big difference between having a fixed end and open and a free end is that at the end, if it's a free end, it's always going to be an antinode, right? At a fixed end, it's always going to be a node, right? Based on the phase change idea, right? Reflection and phase change, okay? So reflection with phase change and no phase change is canon to IB, right? That means it's a core thing that the IB wants you to learn. However, in one of the May 2025 papers, I think IB made a mistake, and I think they're refusing to admit that they're wrong. Okay, there was a reflection question, and I believe all the students all thought there was going to be phase change. Turns out the answer said that there's no phase change, right? Which is freaking annoying because it's like they are very inconsistent with it. If you look at all the past year IB papers, they always said that at a fixed end there's always going to be a phase change, and then now they decide to say that there's no phase change, right? They're not consistent. It's really quite frustrating, right? Let's see what the examiner's report talks about if I can get a copy of it, right? One day. Okay, anyway, there you go. You also still get your standing waves. Okay? Right. Yeah. So I did mention that you can't just simply shoot a wave out and then make it come back and then say that there's going to create a standing wave. Right, so let's do this now. Okay. I'm going to give you a string. Okay? I'm going to start off at a very low amplitude. I'm going to start off with low amplitude of 0.1 cm, right? It's a very, very low amplitude of 0.1 cm. I'm going to start off with zero frequency, right? No damping, of course, tension is 80%. Now, here's the thing. You have to remember that for waves, the speed of the wave depends on the medium. So this string has a tension of 80%. I'm leaving it at 80%, right? Means that the speed of this wave inside this string will be a constant value. It won't be faster just because I increase the frequency. The speed will always be constant. So if I don't change this thing here, the speed, the v equals f lambda, the v is constant. So what will happen when I increase f? Right? Lambda will decrease, right? So you understand that, right? V equals f lambda. You increase f, lambda will drop. Okay, good. So right now, I'm going to then start to increase the frequency because I want to get a standing wave in this simulation. Okay? So I'm going to try to increase the frequency. Now, I know exactly which frequency to do. So I'll give you a random one first. I start from 0. I'll tell you that I increase to 0.23 hertz. And let's see whether it can get me a standing wave, right? This is slow motion. It's quite annoying, right? So let me make it a bit faster. Okay, there we go. Right, I want to see whether or not we can create a standing wave from this. Yeah, it doesn't look like it, right? Yeah, it doesn't look like it. So essentially, I'm not getting effects of a standing wave, right? Sure, I see some movement of the string, but I'm not really getting an antinode effect, right? So if you already have attended this in school before, you should be aware of things like first harmonic, second harmonic, third harmonic, okay? Technically, you're not supposed to be using the word fundamental frequency. So if you hear the word fundamental frequency, you have to tell your teachers that that's actually not in syllabus, right? But you should be following the first, second, third harmonic, right? Yeah, I'm not seeing it, right? Okay. What I'm gonna do now is we're gonna increase the frequency. Again, I started from 0. I increase the frequency bit by bit until I hit a certain frequency where I'll see a very obvious standing wave inside, right? Let me show it to you. Okay, so after with my own testing, right, I figured out that the first harmonic is 0.42 hertz for this particular simulation here, and I'm just going to let it run at 0.42 hertz. And very quickly you realize that I didn't change anything. I didn't change the amplitude. I didn't change the damping or the tension. I just merely changed the frequency. I started from 0. At 0.2 hertz, there was no standing wave. At 0.42 hertz, suddenly there's a standing wave. Right? This is a hallmark of a standing wave. All right. What you can see is that there's an antinode. There's a very large oscillation up and down like this. This is your first harmonic. Okay. Yeah. Some of you might argue saying that, hey, how come this particle is moving? Now this particle is moving because it's just part of a simulation. Right? They attach it to the oscillator. So as the oscillator vibrates, right, they definitely moves up and down, but this is also considered fixed end. So this system that we have here is one end fixed, another end fixed, both ends fixed. And in a while, you realize that, oh wow, this thing is going a bit haywire now, right? So you are getting this very, very large amplitude. Okay, so this is what we call the first harmonic. What's the shape of the first harmonic? In terms of wavelengths, what's the shape of a first harmonic? In terms of a wavelength, what's the shape? Half. Good. It's half a wavelength. So the first harmonic, right, for both ends closed, is half a wavelength, right? Because it's like there's one giant curve here, and then there should be another one there, like this. Okay, let me give you the long story short. Standing waves is you adjusting the frequency so that you can fit the correct shape between the two ends. So the first correct shape that you can fit nicely between two fixed ends, that means two ends at equilibrium, is half a wave. What's the next shape? One full wave. What's the next one? 1.5. Then the next one, 2. The next one, 2.5. Right? So your job is to just adjust the frequency until you can get the wavelength that will fit into the string. Then you can get your standing wave, then you can get your first harmonic. Okay? Right? So you might be thinking, some students that never experienced this before might be thinking that, aren't you just increasing the frequency and therefore you're getting a standing wave? Hell no. Let me try to increase this up to 0.5 something, right? So let's say I do like 0.5, right? 5.1 for example, right? Then I let the program start again. Let's see, right? Higher frequency now. Can I get a standing wave? Let's see whether we can get a standing wave. Not really, right? You don't see like very obvious features of a standing wave. There's no antinode. There's no like another node, right? And the amplitude is not big, right? So it's not about like, oh, you just increase the frequency, right? Just throw any random frequency in or just throw a wave in and therefore you get a standing wave. Ain't not gonna happen, okay? I'm gonna ask you this though. So the first frequency was what? The first frequency we used was what? 0.42 hertz. I mean, the one that we can get a harmonic, right? The first harmonic frequency was 0.42 hertz, right? That gave me half a wavelength, right? What's the next one? 0.84. 0.84. So I'm going to try to increase this up to 0.84 hertz and see whether or not we can get the second harmonic. Right, so 0.84. Okay, let the system restart again. Right, and then we see, so what we're expecting to see? What's the shape? Sine. You know why sine? Because both ends are supposed to be fixed at equilibrium, right? Yeah. So we should see a sine. We should see one full wavelength, right? Doing a standing wave like this. Okay. So now this particle in the middle is supposed to be a node, but because this simulation is so realistic, in compared to real life, this particle here is very close to being a node, but it's kind of like still wobbling up and down. Doesn't matter. We just approximate it to be to be a node. Okay, so there you go, right? So this is your standing wave. Okay, right. And one more thing I need you to remember is this. So what's so special about having a standing wave? Like, what's the whole point of having a standing wave? Like, so what if it's a standing wave? So the thing is that it's a big deal back in the I don't know, the Victorian age, right? When they were making instruments, violins and cellos and double bass and all that. Those were like the days where they didn't have digital amplifiers or microphones or anything like that. They needed their instruments to play music that could amplify itself to the theater, right? Like a stroke of the violin, like the sound can go through the entire theater, right? That's the whole idea, right? So what they had to do was they had to ensure that you can get a standing wave, because what's one of the features of a standing wave? The amplitude. Look at the amplitude. Amplitude is huge, right? The amplitude is huge, okay? So what does this mean about the sound that it produces? I mean, this is the wave lah. This, like, let's say this is a guitar string. What does this tell you about the wave, the sound that it produces? It is louder, right? That was the whole point. Resonance is this. This is resonance. So if you hear things like this, standing wave, is this a standing wave? Yes, it is. Which harmonic is this? Second harmonic. This is a second harmonic. This is resonance. That's why C4 is called standing waves and resonance. This is a form of resonance. Your instrument is resonating, right? But you must get it at the right frequency. You cannot just like, oh, I just increase the frequency indefinitely and can get a standing wave. Right? Tell me, what's the next one after this frequency? It's 1.26. Yeah, 1.26. So we try for 1.26. Okay, 1.26. Right, and then we let it run for a bit. Okay, so in a while, I can't speed this up. You know, it will get there. But in a while, you can see, oh, you know, very obvious signs of nodes, antinodes, 1.5 waves, increased amplitudes, right? This is fully formed standing waves. So for those who are doing standing wave experiments, right, you have to do this. You kind of like, hang on, right? You have to do this. You have to adjust your frequency back and forth by a little bit, maybe 1.27, maybe 1.24, right? You have to adjust it back and forth a bit, right? And then you have to observe and see whether or not you truly get the biggest amplitude, right? Only when you get the biggest amplitude, like within this range, okay, then you can conclude that that's the harmonic frequency, all right? It's the same thing for those who are doing the wine glass. Anybody doing the wine glass experiment? Right. So if you're doing the wine glass experiment, you want to hear a very loud sound from the wine glass, right? Because a very loud sound will indicate that it's resonating. It will indicate a standing wave. So when you do this kind of questions in the exam and you have a standing wave question and they say that, oh, the instrument is producing a loud sound, it's this. This is the loud sound. Because this is the string having super high amplitude. So the sound that's producing is loud. So what you hear is from the outside. They're not saying that the loud sound is here. Like, you're not putting your ear to the string like this and you're trying to hear a loud sound coming from the middle of the string, right? That makes absolutely no sense. You can't hear a string, right? A string is a transverse wave. That's not what you hear. What do you hear? You hear sound. So this string hits the air particles and the air particles vibrate, and that's what you hear. The entire string is doing that. So you're hearing a loud sound from outside of the string. So as I'm standing here, right, you know, I imagine this is a guitar string. I'm actually hearing a very loud sound from the guitar string. Okay? All right? So that's what a standing wave is. A standing wave is a form of resonance. Okay. Again, I am going through this very quickly. Obviously, I'm trying to condense everything into one short session, if I can. Right? If you still don't understand any of the things that's going on here, I can show you the original recordings, all right? So don't worry about that. Okay, this is just a matter of like, for those who are attending today, right? See whether or not you can recall all these little facts here. Okay, what happens if I change it to a loose end? What happens if I change it to a loose end? I reset the system, I go back to 0 again. Okay? Just now, when it was a fixed end, Just now when it was suffix n, the first harmonic was what shape? The first harmonic was half a wave, correct? But now it's a loose n, which means that this n will be an antinode. So what's the most basic shape that you can get to get resonance in one end fixed, one end open? A quarter of a wave, right? A quarter of a wave, which means what is the frequency? Just now was 0.42, right? This one will be 0.21, right? This one will be 0.21. So if I adjust this to 0.21, oh, sorry, 0.21, and then I let it run, okay? So don't forget, this end here is loose, so it will be an antinode now, and therefore you will expect the first harmonic for this to be 1/4 of a wave. Can? Alright, so 1/4 wave, and then you predicted that it will be 0.21, so I adjusted it to 0.21, and therefore there we go. Right, this is the first harmonic of one end closed, one end open. Right, 1/4 of a wave. The question is, what's the next one? 3/4. The next one is 3/4. Yeah, 3/4. How about double the frequency? What happens if I use 0.42 like just now? You know, I go with 0.42. What do I get? I should get half a wave, right? But can I fit half a wave into this system here? Why not? Half a wave means that if I one end fixed, right, the other end must be also fixed, right? Correct or not? Okay? But this system is what? One end is fixed, one end is open, right? So can I fit half a wavelength into this system? I cannot. Look at that. I put 0.42. I can't get a standing wave out of this. Right? So basically the first harmonic of a one end closed, one end open system is what? 0.21, right? So what's the next one? Times 3. 0.63, right? 0.63. So the next harmonic is actually 0.63. All right, so I'm gonna read, like, change it back to 0.63. What's the shape again? You said how many of a wavelength? You should see 3/4 of a wavelength, right? So let's let the system run for a bit, right? So do you see 3/4 of a wave now? You do, right? Okay, good. So you got to remember this, right? One end closed, one end open. The system goes in odd number quarters. 1/4, 3/4, 5/4. Right? Looks like you all understand this. Okay, like not as bad as the single double slit problem, right? This one's okay. Okay, good. Right? I'm hoping those online are catching on to this. If you are catching on to this, then I can quickly fill this up already because, it seems like these guys are okay with it. Then I'll go through the more difficult bits of standing waves. Okay? So these are both ends closed. Look at this. This is both ends closed systems. There are 3 of them. First harmonic, second harmonic, third harmonic. We'll draw them very quickly. This is both ends open. Now, both ends open is not a string. You can't get a string where both ends are open. That don't make no sense, right? So it's a sound wave. So you like both ends open. Now the thing is that mathematically, both ends open and both ends closed have the same math, right? And then you have one end closed, one end open. One end closed, one end open will go by quarters in odd numbers. Okay, so very, very quickly, let's draw it all out because, it seems that you guys know this. So like I say again, I will do it like on the pace of like your understanding. All right, so if you understand this, then great. Okay, so this is a note, this is a note. First harmonic, what's the shape? Oh, it's like my head over here. Okay, right, so it's half a wave. When you're drawing standing waves, you must always draw the dotted lines because the dotted line will represent, right, that this wave will be like this, then later it will be like that, then like this, and then like that. Just like the string that you saw just now, the animation, right? It will just keep on going up, down, up, down, like this, right? The middle here will be antinode. Do not mistake, antinodes is maximum displacement. So even if the wave is pointing down, right, that's still an antinode. Okay, what's that next one? Node, 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 node. Right, one full wave. Okay, this is second harmonic. So second harmonic, right, this is first harmonic. Okay, seems like you guys are quite adept at this, so I'll go through this really quickly, right? If anyone who's online needs me to pause or needs to ask a question, please do so. Otherwise, ask me for the more detailed explanation in the original lessons. Okay? All right. Okay, this is the third harmonic. Right. Okay. Then this one here, the length of the string. So even though the string looks like is a curve, the length is still considered as the length across the equilibrium. Right. So the L is equals to half lambda. Right. The L is equals to half lambda. The L here is equals to lambda, and this L here is equals to 1.5 lambda, right? But the lambdas are all different because this is the first harmonic, second harmonic, third harmonic. So I'll call this lambda 1, lambda 2, lambda 3. Okay? Right? And then what's more important is actually the frequency that gives you this harmonic. Right? So this is F1, this is F1, this is F2, this is F3. So there is a general formula that doesn't appear in the data booklet. The general formula is this, right? For the nth harmonic frequency, it is NV over 2L. Okay, NV over 2L. That's the general formula. N is the whichever harmonic they're looking at, nth harmonic. Okay, V here is the speed of wave. Okay, so if it's a string wave, we might not know the speed unless they tell us, right? But otherwise, we need to use the speed, right? And L will be the length of instrument, right? Be it a string or air pipe. Okay, so this is the general formula for both ends open, both ends closed, / both ends open, both ends open. Right, there we go. I'm going to screenshot this for you, right? Because I don't know those online, are you very quick at copying? If you're not, right, you might be a bit behind. Right, so I'll move on to the next thing. Okay, next one. Both ends open. Both ends open means what? At the open end, it must be a antinode, right? It must be an antinode here. It must be an antinode there. So the first harmonic is half a cosine wave because that's the first shape that you can fit in, right? To one end amplitude, the other end amplitude, and then you need to draw the dotted line to show you your the standing wave half a period later, right? And the node is in the middle here, right? So there you go, right? And then if it's second harmonic, right, it looks like that. Okay, technically speaking, you don't really have to draw it. Like they hardly have asked any students to draw it over the years, right? So we're just drawing as a formality, right? Yeah. Actually, I also don't know why I make the students draw all the time. So like I'm quite sure you have drawn it in school also. You know, that's the thing, right? It's the weird thing. You have drawn it in school all the time, right? Okay, so blah 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 blah. Both ends open. Let's not waste any more time. Fn, general formula for nth harmonic frequency for both ends open. Both ends open, right? It's the same as the one before. Fn is equals to NV over 2L. Okay, that's it. Right? N is equals to 1, 2, 3, 4, 5. 2, 3, 4, 5. All right, and very quickly, let's go on to the next thing here. Right, I will do this later. I'll do this later. Okay, right. Yeah, I'll do this later. Then we just jump into one end open, one end close. So when it comes to one end open, one end close, the mathematics is different, but the kind of like the fundamentals are the same. Closed end has to be closed end must be a node, open end must be an antinode, and therefore the first shape that you can get is a quarter of a wave. So we draw a quarter of a wave like this. So this is 1/4 of a wave like that, right? So the L is equals to 1/4 of lambda 1, right? But when it comes to the second harmonic, one end closed, one end open, right? It has to be 3/4 of a wave. So this 3/4 of a wave. L equals to 3/4 of lambda 2. Sorry, not lambda 2. So the tricky bit for one end open, one end closed is that there's no even numbered harmonics. It's all odd numbers. So it's 1, 3, 5, 7, 9. right? So even for the last one here, this is like 5 quarters, so 5 over 4 lambda 5, right? So you have 1 1/4 wave, right? Something like that, right? So it look like that. It's a node and it's an anti-node. Yeah, yes, that's annoying, right? So then the general formula, right, for Fn, 1n open, 1n close, 1 open, 1 close, 1 open, 1 close, NV over 4L, but the N is 1357. Right, so that's in odd numbers. Okay, can? Yeah, yeah. I'm breezing through this because technically speaking, they don't actually ask this very often. Like they don't ask you for the general formulas very often. They actually ask you all the weird ass application stuff. But if you can't get this part through your head, it's actually very hard to understand the application stuff. So that's what I'm going to do now. I'm going to do the application stuff now. Okay. So one of the applications is this. Okay. Uh, hang on, Right. I know it says draw the fourth harmonic. I'm not going to do that. I'm going to tell you this. There's some sand at the bottom. There's some sand at the bottom. There's a fourth harmonic passing through. So I'm going to draw for you the sand. Fourth harmonic means what? Means two full waves, right? Right, two full waves. So one. So 2, 3, 4. I think something like this. Let me just try to rearrange it a bit. You may wonder what the heck is that? Is it nicely even? I don't know, man. Okay, yeah. Yeah. Yeah, correct. Yeah. Yeah. So when you have the fourth harmonic and you have some sand at the bottom, so anyway, that's sand, right? Some sand at the bottom. The sand will make little like heaps like this. Like what does it represent? Yeah, right. The sand will represent the nodes, right? So if you draw your fourth harmonic, which is one wave here, right, like this, and another wave here, right, like that, right? Then the sand piles will represent the nodes. So you cross wherever you cross at. This is where the nodes are at. Okay, so these are nodes here like this. So why does the sand pile up at the nodes? Yeah, why do the sand pile up at the nodes? Yeah, weird question. So at the nodes, what are the air particles doing? Okay, hang on. I haven't showed you a standing sound wave yet. I mean, insofar, you've only seen a standing string wave. This is a standing string wave, guys. Look at that. The standing string wave. All right. It's a transverse wave. So while the original waves the incident and reflected waves are traveling left and right, okay, the particles are actually moving up and down. So this is the transverse wave. It's a transverse standing wave, or it's a standing transverse wave. Let me show you how a standing sound wave looks like. Right? This is a standing sound wave. Look at that. That's a standing sound wave. Like this picture here. All these black dots here, right? Sorry if you have trypophobia, right? All these black dots here are air particles. And these are how the air particles move when you get a standing sound wave. I mean, how do the air particles move when it's a longitudinal traveling wave, right? It looks like this. And let me show you side by side then. You know what? Let me show you side by side. Okay? This is a traveling wave, right? You can see the wave traveling towards the right side. Yeah? But then once you create a standing sound wave, this is how the standing sound wave looks like. You see the subtle differences? Yeah? but the features are all still there. So a standing wave has nodes and antinodes. Look at some of the particles. Look at this guy here. He's not moving, he's never moving. That's a node. Then this guy here, when he moves with the biggest amplitude. Right? That red dot there is an antinode. Right? You don't get that here. Like they all move. Eventually all the particles move the same sort of amplitude and the same sort of like period and phase and all that, right? So they all, yeah. What, this one? Yeah, look at them. They're all moving on. They're all traveling back and forth. I mean, they're all oscillating. Sorry, the proper word is oscillating. They're all oscillating. You know? Yeah. Right. There's no point at all on this diagram here where it doesn't move. Right. All of them are always oscillating. This one here. Right. Look at that guy there in the middle. Okay. Right. Okay. I also want you to notice this. Yeah. Like, what do you notice about the compressions here? Like, compressions are easy to look at. What do you notice about the compressions? The compressions are always moving. Right? You see the compressions are always moving. Right? The compression is traveling towards the right side. Look at this. How about the compressions here? What are the compressions doing? Compression, rarefaction. Compression, rarefaction. In fact, where do the compressions happen? Yeah, the compressions always happens at the nodes. Right? Look at that. This is the node, the compression. But it happens half a period each time. So half a period is a compression, then the next half rarefaction. Compression, rarefaction. Compression, rarefaction. So that's the big difference between the two. Yeah? Okay, you understand that? Yeah, there we go. So that's the one key thing of difference, right, about the two. Right, you got your standing waves. Yeah. Okay. So back to my same question. Why does the sand pile up here? Because at the nodes, the air particles are not moving. Right? They're not moving. So if there was sand on the side here, the air particles would have swept the sand side to side. Right? The air particles oscillate back and forth, right? Right? And they will sweep the sand side to side, and then it will just form piles at the nodes. Okay? So there you go, right? So basically the sand forms the piles at the nodes because the air particles are not moving there. Right? So there you go. So if you had some sand over here, like you put some sand inside the tube here, the sand will just accumulate here. Because if you had some sand here, right, you see the air particles would have just pushed the sand side to side like this, right? Until they all accumulate at a certain point, right? That's a heap of sand there. Okay. So here's the thing. How does a standing sound wave actually look like in real life? Can you see it? Can you see a standing sound wave in real life? You can't, right? You can't see a standing sound wave in real life, right? Like if I had a standing sound wave in this pipe, you're not going to be able to see it. So there are ways to visualize it. One of the ways is to put sand in it, right? So if you put sand and they form little heaps inside the tube, you can measure the distance between the two heaps, right? I'm going to ask you this though. What happens if I were to measure this and I tell you that this is 10 cm apart? Okay? And then I tell you that the speed of wave v is equal to 340 meters per second. Can you tell me what is the frequency being played now? What's the frequency used in this experiment now, given that the distance between the two heaps is 10 cm? So the wavelength is how much? Yeah, so the wavelength will be 0.2 meters. It will be 20 cm. Because between two nodes, right, a node and a node here, between two nodes is half a wave. Right? It's half a wave only. So between two antinodes or between two nodes, it's only half a wave. You get that? Okay? Right? And therefore, what's the frequency that we use? V equals F lambda F is equals to V over lambda, 340 over 0.2. What's the frequency used? What's that? 1700. Is that right? 1700 hertz. I don't know, man. Check your math. You're trying to Kumon your way out of this. Is it 1700? Damn. You took Kumon? No, right? Okay. You can mentally calculate this shit. I cannot, man. Anyway, so yeah, 1700 hertz. Yeah, there you go. Right. So if you had to go and find what frequency was used, you can use this method. Or you could control the frequency, get the harmonic, right? Measure the distance between two heaps of sand, and then calculate the speed of sound. They could ask you to calculate the speed of sound as well, right? Anything happen. You just depends on like what they want you to find, right? You just need to realize that this is a relationship here. Any issue so far? No issue so far. Okay, good. All right. Other questions like these ones here, right? This ones here, I believe I've done before in my previous class. Please ask me for the recording for these questions here. This will be your homework, right? I'll leave it to you, right? There will be questions like this, right? So you will realize that all the questions here don't actually deal with that general formula, the Fn equals to Nv over 2L or Nv over 4L, right? They don't use that. They actually ask you to count waves instead. Like say for example, look at this. Microphone, 5 meters along a standing sound wave from a node to another node. In between there's 16 empty nodes. Right? So your job is to go and calculate how many waves is that? Right? So how many waves is that? I mean, might as well, right? So from one node to another node, 16 empty nodes in between. So how many waves is that? From a node to another node, 16 empty nodes. So you're basically doing wave counting, right? Let's say you had a node and then another node, right? Between two adjacent nodes, how many antinodes are there? You have only one antinode, right? But the question says that you have 16 antinodes. 16 antinodes, right? So how many waves is that? 8 waves, 8 wavelengths, right? Yeah, 8 wavelengths. Because in order to get one full wavelength, you need another antinode, right? You need an antinode. So another way is one full wave has 2 antinodes, 1 and 2, right? So 16 means 8 wavelengths. There you go, 8 wavelengths. And then you can find it already, 5 divided by 8, and then go and find the answer, right? I'll leave that to you. I won't care about this, right? What's very important is sound waves. How do the particles move? This is very important. I need to go through this now before you all go and start thinking, your own version of the standing waves part, right? So that's the thing I need to ensure now. I need to make sure that you guys get it. Okay. So in order to do that, right, I want you all to draw a nicer, right, nicer second harmonic of a sound wave. Okay. Right. So I want you all to draw a nicer second harmonic. So draw a second harmonic here. No. Yeah, let me just. No, they just find some space. I'm just gonna connect it like that. Yeah, there we go. This is a second harmonic. You got that? Yeah? It's a standing wave, so I need to draw the dotted line. Oh, I can't dash this thing. Shoots. So no choice, I have to freehand this thing. Okay, hang on. Okay, something like that, right? Okay, number one, let me ask you this now, right? Right now, the shape of the wave is the solid line. Okay, half a period later, how does the shape look like? Half a period. So now it looks like this. Half a period later, what does it look like? It looks like the dotted line. Yeah. So in half a period, the wave will change, will flip over to this side. Then it will look like this instead. You understand? So if you start off like this, then half a period later, it go down like that. Then another half period goes up and down like this, right? Okay. So it's kind of like this GIF here, right? I'll show you the GIF here. This one, right? Like this. You just cut to maybe something like that. You see that? Yeah. So it will look like this, right? So start here, half a period, one full period. Goes back to original, right? Okay, so one more time. If you start here, half a period will be here, one full period will be here, another half here, one full period will be there, another half here like this. Correct? Which is why we draw standing waves with the dotted line and the solid line together. Right? So I undo this one first. So this is how it looks like. How about 1/4 of a wave? How does it look like in 1/4 period? 1/4. So go from here to there, that's half a period, right? 1/4, flat line. 1/4, it will look like this. Right? 1/4 period later, it will look like that. This is 1/4, sorry. Right? This will be 1/4. Like it will look like this. Right? It will be a flat line. Okay? So just understand, this has happened in IB like 2 or 3 times already. It's quite funny one. Like every time they ask students, draw the line to represent the shape of the wave 1/4 period later. Then 1/4 starting from that shape will be this, a flat line. Okay? In case you need a bit of more proof on that, right? You can try this one here. Right, so this is the standing wave, and then 1/4 period looks like this. Then another one more quarter, it flips over to like that. Then 1/4 again goes like that. Right, so at some point the shape will look like this. Right, that's every 1/4. Can? Wait. Okay. So this is a standing sound wave. It's a standing sound wave, which means that the particles involved here is what? What kind of particles are they involved here? Sound wave. So what kind of particles are involved? Air particles are not sound particles, okay? All right. So let me draw for you an air particle there. There's an air particle here. I'm gonna ask you this though. What's his displacement now in this picture? Right? You see that this one here shows you greatest amplitude, right? But don't forget, sound is a longitudinal wave. So sound travels in, hits this end, reflects back. You get a standing sound wave. The particles are supposed to oscillate parallel to the wave. This is not a string wave. This is not a transverse wave. This is a longitudinal wave, a longitudinal sound wave, which means that when the graph is like this, the particle is at the right side, has displaced to the right with amplitude. This is the antinode particle, and the displacement is maximum here like this. So this is max amplitude, which is this value here. Like, no, this value here is the maximum amplitude. So for a sound wave, please be very, very clear on this. For a sound wave, a standing sound wave, this blue line is a graph of displacement. It doesn't show you the actual position. If it's a string wave, yes, the string wave looks like the graph itself. But if it's a sound wave, this solid line is only just the graph. Okay? So I need you to take some time to understand this, because if anything, even if you understand what I described earlier in today's class, right? This is the part where it kind of like confuses the students the most. Okay, let me show you this. This is the actual standing wave. but this is the graph. Look at how the graph is moving. The graph is moving up and down, up and down. But the particles are actually moving left and right, left and right. You see that? So I want you to kind of like see the pattern here. See, I'm gonna track this red color particle in the middle here like this, right? I'm gonna trace with my left hand the graph. Okay, so it's to the right, then to the left, to the right, to the left, to the right, to the left, like this. Okay, right? So it's basically moving maximum to the right and maximum to the left. In between is equilibrium, right? The equilibrium somewhere in the middle, right? Between where the particles moving left and right at, right? And then the graph will therefore go maximum and most negative, most positive, most negative. Okay? So when you have a standing sound wave, right? You will get a picture like this. They will draw for you the standing wave and they will ask you draw the direction that the particle has been displaced. They love to trick students on this. This has happened many times in IB already. They give you a standing wave like this. They draw for you the graph. They're just waiting for students to draw an arrow up. You draw an arrow up, you lose the marks. And then you're like, why? Right? So the particle has displaced to the right. Okay? How about a particle here? How about a particle here? So according to the graph is the most negative, right? So which means that this particle has gone where? To the left. So it has maximum amplitude to the left. Let's try another particle here. Let's see, we try one particle here. So when you look at the graph, it's also negative, but not as much as that one, right? So then you draw an arrow here like this. Shorter arrow, but to the left. Right, how about a particle here? Also negative, and therefore the short arrow to the left. Okay, short arrow to the left, right? How about this one here? Short arrow to the right, good, right? So there's a short arrow to the right, like that. Okay, how about on this side here? This one? Max arrow to the right, because positive, right? No matter what, the graph is positive. So this graph, you see this graph here, all right? There's an equilibrium line in the middle, right? Anything above the equilibrium line is positive displacement. So all these particles are all pointing towards the right, right? All the particles within this region are all pointing towards the left, right? And all the particles on this side here are all pointing towards the right because they all have positive displacement. So you will draw it like that. This is maximum amplitude, right? Like this, right? You see, I mapped out all the particles for you. Do you notice any special features about the particles that I've just drawn? What do you notice about this region here? Yeah, it's a compression. It's a compression because all the particles have all, moving towards the center here. This is a compression. This, rarefaction. There you go, right? So this is compression right now, and this is a rarefaction right now. Okay? Right? Yeah, there you go. So excellent, right? So you get the hang of it. Right? You got the hang of it. Let me try this though. Let me try this. What happens if half a period later it goes like that? Right, half a period later, it becomes like this. Yeah. Right, half a period later, it becomes like this. So what will happen then? Yeah, right, the arrows will all reverse. Right, they'll all go the other way. Around, right? So what we have is, you're going to get, right, particles that look like this. Right, then this one here, right, the compression will become rarefaction, rarefaction will become compressions. You got this? Yeah, this is one of the most important ones, because this one here is the one that kind of like students don't understand. Like, how come the graph shows me is upwards, but then yet the particles are moving to the right and to the left? And that's because it's a longitudinal wave. If it was a string wave, then the shape of the graph is the shape of the string anyway. We good? Yeah, it's been 2 hours and 10 minutes already. You guys are holding on strong still. All right. But I think I am more or less done with standing waves. Okay, I think I'm more or less done with standing waves. So the next big problem would actually be damping as well as free force oscillations as well as Doppler's effect. But I think I really don't have time today, right? And I did say that I want to hold a 2.5 hour lesson, but I also have data consults that I need to settle. So I think I will stop here because if I were to go on to free and false oscillations, that's going to take me another half an hour. Yeah, this will be like super long already, right? So I'm gonna call it. I will continue next week, right? I'll hold another one more lesson for y'all next week, right? Anyone going overseas next week? Oh, okay, you're going to France. Okay, Paris is it? First time? Not first time? Do you like Paris? It's okay. Yeah, I hate it. No, I hate it. I hate it, man. I seriously hate it. Sorry, the airport train smells of piss. There's dog shit everywhere on the main streets of Paris. And every time I go out and I walk, right, some guy will say, "Hey, you from China?" I'm like, "No, I'm not from China." Yeah, sorry. Paris sucks. I'm sorry. Yeah, and it's not the first time there. Why the heck you going there again? I will never go there again. Oh, okay. Oh, that's fine. That's fine. South of France is nice. Yeah, Paris sucks. Okay. Anyway, those online, I think that's it for today. I really cannot. I really shouldn't start on the next thing. Okay. But I have a half a mind of just dropping you all this video for the free and false oscillations. Yeah, cause it's just gonna take half an hour, and I'm like I really just want to pay attention to Doppler's effect next. This thing, free and false oscillations, is actually quite mutually exclusive from standing waves. It's like standing waves and free false oscillations has actually no bearing on each other. This C4 is a weird chapter. It's a very distinct cut in between. In fact, free false oscillations belongs to SHM. Yeah, it belongs to simple harmonic motion, but I don't know why is it doing here, right? At my A level side, I teach this together with my SHM parts. I have no idea what this is doing here. Anyway, so I'm gonna wrap up today's lesson. I'm gonna stop here. Let me just tell you this. This is your homework for standing waves, right? Get this done, right? Obviously, if you don't know how to do some things, right? There's a lot of work to be done outside of class, and especially those who join later or those who are playing around, like in earlier parts of year fives, right? You would have to do the work, right? So you look at the Telegram. There have been people asking some questions already. I mean, that's actually only Julian, right, so far. But he's starting to do some of the questions and starting to do some of the work, right? I don't know how else to emphasize to you guys. Do you understand this? Like, you have to do some work outside of class. You cannot just attend the class and then just say like, oh, as long as I listen, can already. Ain't gonna happen. That never ever works. So you have to do the questions. The only big thing is that I don't monitor you. Why you're packing up? Data consult, sit down. So I can't hover over you to do your practices. So you have to do the practices. You know what? I tell you what, I will assign actual questions. I'll type it out in a group chat and tell you specifically what you need to do so that you will go and actually do it. Otherwise, it will never happen, right? So I better tell you specifically which are the questions. All right? But if you still don't do it, even after I've told you specifically which ones to do, then all I can say is that really is on you, right? I cannot help you otherwise after that already. I will still support you, see? It's just that I don't hover over you. All right. So those who are online, I'll see you again. 2 hours 15 minutes. I'm done here today. All right. See you guys. Bye bye. Those online, see you. Bye bye. Thank you.